Guys, let's talk projectiles again. All right, finish out this first week of projectile motion, and let's take a look at where we've been. So we started off looking at your workbook. We did a little bit with some practice problems, the worksheet 1 to 5. All right, worked our way through that. Those are actually in the last video. So if that is something that you need to go back to, definitely do so. It will help you out. Took a little bit of notes about horizontal projectiles in particular, projectiles in general, what that means, the fact that we have a horizontal component that is independent of the vertical component. That is really important for us to know. We never accelerate in the horizontal. We only accelerate in the vertical. And so the time that we spend in the air is dependent upon how high the object is, like how high off the ground the object is. So, you know, the cliff height, the diving board height. Let me write component here before I forget what I'm talking about and spell it wrong or something. All right, but these two are independent of each other. All right, we've got little g, we've got acceleration going on in the vertical. We have no acceleration going on in the horizontal. That is really important to remember. Now over here, we sometimes have initial velocity in the y, and sometimes we don't. That's also really rather important. If our initial velocity in the y direction is 0, we are dealing with a horizontal projectile. And that is what clarifies that type of a problem from a problem where your projectile is being launched at an angle. So that is something that you need to remember. If your initial velocity is not 0, that's because you're being launched at an angle. And that angle will be given to you in the question. In which case you're going to bust out your trig and figure out what that value is by using the sine component 99.99% of the time. Okay, so that kind of clarifies where we've been. So you guys were working on practice problems 1 through 5. Before we did practice problem number 5, though, I said, hey, let's play around with the projectile launcher. So we started off, and I gave you this. Here was our desk, and here was the projectile launcher, and we shot the ball, and it hit the ground along these lines. Looked like that. Okay, and so I said, hey, go shoot the ball a few times, and you all did, and you went a little bit crazy, and it was lots of fun. And I said, then I took the ball away and said, now I want you to figure out the velocity of the projectile launcher, and I let you loose. So what you guys were doing is you took some measurements, these are out of memory, so I'm not really sure exactly how accurate they are, right? But you measured the distance from the launcher to the landing position, so you figured out the range, and again a reminder that that's what we call this, the range. All right, 2.79 meters, and then you measured the height of the table, which was, I think, about 1.02 meters. And then you did a little bit of math and figured things out from there. And if I had been smart, I would have done that on the next slide, so I wouldn't have to redraw it, but I will. I'll redraw it again. All right, so 2.79 meters, 1.02 meters, and of course the ball made a half of a parabola. And so then the next thing I said to you guys to do was to make some graphs and figure it out, and lo and behold, you did. All right, so I said, what's happening in the x direction? You guys all figured out it was moving with a constant velocity. Now let's think about that in terms of what is happening with our projectile and arrows, because you see this a lot in MOPS, and I know some of you are struggling. What this means is that at every point along this path, you have approximately the same. I'm trying to draw those all equally. It may not be perfect, but it should be close. All right, so whatever my x velocity is, it's the same all the way through, which is what you're telling me when you do this line like that. Okay, we don't know the time in the air. We got to figure that one out. We do know how far it went. It went 2.79 meters, and that's the area we have under the curve. Okay, ultimately, I'm asking you to figure this out, but so far we can't do that quite yet. We need a little more information. So let's change over to the y direction. This is where I see a lot of you making mistakes now when you're doing your WebAssign or when you're doing your mobs, is you're struggling with this graph. All right, but ask yourself, when this leaves the table, what is the value of the y velocity? Well, it doesn't have any. It pointed straight, left to right, horizontal, completely horizontal. So our initial velocity in the y is 0. What will happen as it moves is its velocity is going to change and it's going to get larger. And how is it going to change? It's going to change, think about this, right? It's going to change by approximately 10 meters per second every second. That's the definition of acceleration if you didn't notice, right? We know that little g is negative 9.81, but I'm rounding it to make my life a little bit easier here. So let's just pretend that I did this perfect diagram here, where this is at 1 second, 2 seconds, 3 seconds, and it's not by any stretch, not with these values. All right, 4 seconds. But what that would mean is that, all right, if I don't have velocity here, my Vy in this spot would be 10 meters per second. Here it would be 20 meters per second. Here it would be 30 meters per second. And here it would be 40 meters per second. Now, I'm not saying they are. We were certainly not in the air very long. So this is a little outrageous to state, but I'm just trying to give a generic example of what's happening. And so my acceleration is constant. It's little g. My velocities in the y direction are changing, but my initial velocity in the y direction is 0. What that means when I graph it is it starts there. All right, it's not starting up here, it's starting here. And I went downward with a negative acceleration. So, whoops, that's not really how you draw a triangle, but it's just the edge that's a little bit off. All right, the area under that curve, and notice I made it negative because it's in the fourth quadrant. All right, here is my slope. It's gravity over here. Again, we're going to look for time. We could find the final velocity in the y direction here, but it's not necessary to solve this particular problem. So we started working with the y direction. We knew the most about it. All right, so let's begin. Acceleration equals. We have two formulas that we work with. We're working with an acceleration formula, and we're working with the area under the curve. And this curve is a triangle. So let's start here with our acceleration. Our initial y velocity is 0. Our initial time is 0. So those cancel. And then I move it out of this formula, or out of this fraction, because we make mistakes when we have fractions. So let's get rid of it. Let's work with this one now. Along the base, that's where I get to TF. Down the height, that's where I get VF from. Okay, so negative, so I'm going to move the 1/2 out. Now, another common error that I tend to see is that you guys are multiplying this by 1/2. That's not true. You are either dividing by 1/2, because let's face it, that's a multiplication operation, so you have to do the opposite, right? So you're going to divide instead of multiply to get rid of it. Or you can say, I multiply both sides by 2. That's kind of what I did here. All right, so now we have a nice system of equations, and I'm going to put one into the other. So equals negative 9.81 TF squared. This should not be new for anybody. Now, we've seen this quite a bit. I just need to do some math because I don't know what the answer is. All right, so TF squared equals 0.208. And notice my negatives cancel out, so that is handy because you can't square root a negative number. And our time in the air, 0.456 seconds. Now, this is a real problem. This was the actual projectile launcher that we had. Okay, so that is pretty reasonable. Being in the air for a second is a really long time in physics. So don't be fooled into thinking, oh, well, that number's too tiny. That can't be it. No, that's it. That's it. It takes some space off the ground before you can get rid of that time in the air. All right, so then let me go back to, let's see, black color. If I want to figure out Vx, I'm going to use my horizontal value, and that's going to be my area under the curve is 2.79, and I'm doing 0.456 Vx, and do a little bit of math, and I will have that sorted out. And we got a Vx of approximately 6.1 meters per second. Okay, that's a little fast, I know, from my projectile launcher, but that's reasonable based on the values that I sort of kind of remember from the last time. All right, so then the next step we did is I said, all right, so the velocity out of the muzzle is 6.1 meters per second. And then I said, I took the gun and I tilted it. I tilted it at a 45-degree angle. And I said, now I want you to figure out where the ball's going to land on the floor. And this took us a little bit of time. Now, a couple of qualifiers, right? We moved the launchers to actually below the table on a stack of books because I wanted it to land at exactly the same height. At exactly the same height. That was important. It's a harder problem if it were to go further and land on the floor. So I said, you know, that muzzle speed of 6.1 meters per second, that looks suspiciously like the hypotenuse of a triangle. So let's draw it and let's figure out what is going on. And right away, you all just started jumping all over the trig of that, which is phenomenal. It's just what I wanted to see. It made my physics heart very happy. And so we actually figured these out right away. And some of you got a little unnerved because the number was identical. And was that right? Could that possibly be right? Well, it's a 45-degree angle. So yeah, the sine and the cosine match. All right, another thing I wanted to point out, I went over with it, I picked the 45-degree angle partly to make sure that you were on the right track here, but also because it gives us the best range. All right, if you're going to shoot a missile at something, if you want it to go as far as possible, you want your angle to be 45 degrees because you have that perfect combination of up and over in terms of initial velocity, right? If it's too close to the ground and you say, well, I could go further because I have more x. Yeah, except gravity's going to slap it to the ground pretty quick. If you say, well, I need to get more height, well, then a lot of your velocity goes upward and it doesn't travel as far from left to right. So 45 degrees is the perfect combination. The other thing that tends to happen, again, because of the trig, is that complementary angles, those are angles that add up to 90 degrees, in case you were wondering, you know, if you were ever going to use that definition anywhere else ever again, you are in my class. All right, but the complementary angles also give the same range. What? That's crazy, but it's true. All right, so if you have a 30-degree angle, you'll get the same range as a 60-degree angle, and so on. Pretty wild. All right, so anyway, this becomes important because we need these. But then what happens when you make your graphs is you don't know what to do with the 6.1. You know what? You don't do anything with the 6.1. How about that? Like once you've got your trig pieces, that's all you're using. So this is our 4.33 meters per second is going to be our initial velocity. Again, we want to know the range. We were looking to see how far it would go. We were trying to predict where it was going to land. So we are looking for delta x. That is our ultimate answer. All right, here we do not have a initial velocity of 0. We have an initial velocity of 4.33. So we actually have to start up in the first quadrant, and it goes like this. And this point right here is this point right here. It's the max, which is really, really cool because I know right there that the velocity is 0 in the y direction. It changes every second, slows down on the way up, right? And then it stops and it waits. So 4.33 meters per second right here. Again, this is Vy. And then it comes right back down to the same spot. It looks kind of, I call this the bow tie. It looks like a little bow tie. All right, so it looks like that. And if you land on the same level, right, think about it. If I went up 10 meters, I got to come down 10 meters. These two areas, they match. They're identical. And this is the halfway point. Now don't be fooled, that's not every single time. It's when you land on the same level. If this were something that kept going downward and the parabola just, you know, kept on going down like this, well, then my this would keep going down like this. And I'd have a triangle actually over here that was a lot bigger. I mean, part of it would still match, right? Like to where I got to there. But then I'd have all this extra stuff, which would be down to here. All right, so be careful. Let me put this down and erase some of this because I don't want that. I want it to be in the same level. No, 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 no. Gotta be careful with this eraser so I don't erase all the important stuff too. All right, I don't think I can get up there by VY. I'll mess it up. So I'm just gonna leave that. All right, but this is what my graph looks like. Now, if we look at this from, again, let's look at this from, you know, like what's happening at each point of the parabola. And I'm going to try to hit kind of the same spots, right, from there to there. What's happening in terms of the parabola? Well, whatever my x velocity is, it's the same at every point along the parabola here. Right? Now let's look at what happens in the y direction. I have y velocity on the way up, but gravity changes that velocity. It's going to get slower on the way up. How much slower? Well, it's going to change by 10 meters per second per second. All right, so as you can see, those little blue arrows are getting tinier. At the top, I don't have a blue arrow, but I'm going to try really hard to match the size of these arrows on the way down. Right? They should be mirror images of each other. It's just that the direction is different. Right? This is like it's like a mirror image. It's perfect. Okay? Just I slow down on the way up, I get faster on the way down, but the increments by which I do that are identical. Very, very cool. All right, so mathematically, what do we do? Well, we're going to work with, let's grab my black pen here. So we're going to work with this spot. That's kind of the critical spot right there, right? We're going to figure out what time that is. So what I saw many of you do is say, okay, delta y equals 1/2 base times height. I don't know how high it was. I do know that the base is TF. I do know that the height was 4.33. Alrighty. So I'm still going to end up with two variables there, right? Let me just multiply that quick and see what I get. So I can at least clean it up. All right, delta y equals 2.165 TF. It's not helping me. All right, so let me work with the slope of the line. I know that the slope of the line is negative 9.81 meters per second squared. So let's try that one. All right, so negative 9.81 equals VF. VF is 0. Initial velocity, 4.33. TF is what I'm looking for. Oh, winner, winner, chicken dinner. Here we go. Look, I only missed one thing over here. I got this. Negative 9.81 TF equals negative 0.433 or 4.33 TF. Ooh, and I get a TF of 0.441 seconds. That's right here. 0.441 seconds. So that means the time to there is 0.882 seconds because it's exactly double because it landed on the same level. Okay, so my total time of 0.882, that can go up here because it's the same time as the horizontal over as the up and down, right? And so delta x is just going to be these two multiplied together because it's the area under the curve. And so most of you did this. 6 times 2 times 4.43. And you came up with approximately about, I don't know, 3.9 meters. And it was somewhere around 3.75, I think is where it ended up finally hitting. Okay, but there was some important stuff to come out of that. So some key things to note. This took a lot of our time last week. And even though we're doing multiple different types of problems now, you know, we're doing WebAssign, we're doing MOPS, we're doing a quiz here and there. There's practice, there's extra practice in your workbook. Oh, let's see. I know I put some extra practice problems in here. It's around page, what, 106, 107. I'll write that down. Page 106 to 107. And I have some practice problems in there with answers. Okay, all of the problems, though, are really going to be rather like this one or the horizontal one that we did at the beginning, back at the previous page. Let's see if I can flip it and see it. Or it's going to be like this one. When you have a problem like this, the graphs always look like this. The numbers change, but the general idea is the same. If you launch at an angle, the graphs look like this. Now maybe the second triangle over here, might be different than what you see in this one, but the general idea is about the same. All right, so it's at this point in physics that you need to practice. This is why you have WebAssigns, this is why you have MOPS, this is why you have extra practice problems in your book. And if you are struggling with any of it, bring me something that you're working on and let's clarify it and get it out. But there's no new material here. Like all the important stuff, you've got it. You've got all the key things. And it's not just about, you know, drawing the graphs. I mean, all that math stuff is really good and really important, but as MOPS will tell you, like to know what's happening to the velocity in each direction, which way does gravity go and what does it affect and what about the time in the air? Like that's what usually hangs you up a little bit in the MOPS, and that is kind of, you know, important practice, which is why we are doing the MOPS in the first place. All right, so practice, practice, practice. Bring me your questions with some work. All right, folks, that is us. Hope you learned a little something that you needed. We're going to continue to practice this week. And yeah, we're going to finish this one up by next week.